the dark matter. Please.
Thank you very much. Okay, so this particular talk, what I think I'm going to do is focus on two things. Firstly, I'm going to take you through the details of a few of the experiments that have been conducted over the last few years in order to look for dark matter. Now, there are way too many experiments to cover them in any sort of complete sense. So, as I say, what I've done is just picked a few experiments which I think are interesting to talk about and will allow you to get some sense of the experimental challenges and the way in which we choose to interpret the data. And as you will see, it's not the cleanest process in the world. This is a very difficult challenge. We're trying to fight extremely high backgrounds, potentially high backgrounds. We're discovering new things about the way the sort of solid state or condensed matter physics of the detectors all the time. The reason we end up having to understand these detectors or the solid state physics in such detail is because we're looking for incredibly rare particle events, and sometimes we get misdirected by new solid state effects. But before I go into talking about those specific experiments, I just wanted to, again, try to give you a little bit of perspective concerning the experimental challenge. And I introduced this plot to you once already, and the reason I'm putting it up again is just to really emphasize where we've been and where we're going. So we've been trying to start work in this field when the challenge was to, if this is a lump of germanium or xenon, that would be about 1 kilogram. And in that kilogram, initially we were constructing detectors which at very low energies, this is essentially below 20 keV, below 20 kilo electron volts, we were trying to look at events at the level of tens or hundreds per day, and that was this early period here, and then we moved into a regime where we were looking for less than one event per kilogram per day, and we've moved to a situation where we're better than one event per month. Now, clearly we have to do that in competition with conventional backgrounds, so let me introduce a summary to you of what conventional radioactive backgrounds look like. So if we say that our search region, as I've already mentioned, is very much less than 100 keV, typically you want the threshold as low as you can, certainly at the sort of keV, few keV scale. Most of the signal is below 20 keV. So, the current performance metric, 1 per month, so if we continue with this sort of SI unit of background, which is the per kilogram per day, we're at the sort of 10 to the minus 1.5 logarithmically on that scale. And where we would like to be going is clearly the particle physics is telling us that we may need to be doing as well as 10 to the minus 5 events per kilogram per day. So let's try and get a little bit of context for that. For instance, what is the radioactivity of the typical human being? So I'm afraid this is the photograph I had, but whatever. How many gammas, what is the rate of gamma ray emission from a typical human being? Is it anyone, me or you, any one of you? I think somebody must have a, and this is entirely due to natural radioactivity. It's just the the potassium 40, the cesium 137, the uranium, the thorium, these things that you carry around with you quite naturally. Somebody has to have a guess. Okay. Well, look. The rate is measured it's not per hour or anything like that, it's per second. Okay? And it's actually a few thousand per second. You are emitting a few thousand gamma rays per second. So if you were in proximity to a detector, you know, a kilogram of germanium or whatever, clearly the fact that you're emitting 1,000 gamma rays is going to be exciting this detector at least 10, maybe, you know, just from the radioactivity from you, you're exciting this thing at least 10 times a second. And some proportion of that signal will be depositing relatively small amounts of energy exactly in the region that we're looking for dark matter signals. So that's an emission rate which is per second. And as I said, with dark matter, our standard unit is per day, and of course we're actually trying to get to the you know, per month and per year sensitivity. So there's just simply no way that you could conduct such a search experiment with, I mean, it's not just us, it's basically the natural radioactivity and everything around you. So we have to do something about that. Well, I've tried here again to give you some perspective concerning radioactivity, what the natural levels are and where we're trying to go. So if you take the sort of typical average surface level, then in units, which is, you know, of microgray per hour, say, where a gray is just simply joules per kilogram. For those of you who are not familiar, this is the way we think about radiation. It's, you know, it's very simple, just how much energy is being deposited per kilogram. In this case, as I say, it's per hour. In these units, and I picked them because they do give you a number which is fairly close to 1. So the sources I've already said are uranium, thorium, cesium, potassium. Now radon, I think many of you may be familiar with radon. Radon, and this has only been realized in the last 20 or 25 years, in terms of your typical exposure, in fact radon gas is very significant, probably over half of your typical exposure. It comes from isotopes of uranium and thorium. It's very dependent on where you are in the Earth's surface as to how much is actually boiling out. It is a very heavy gas. It's a noble liquid. We could potentially have built dark matter detectors out of it because it does scintillate, but it has a very short, you know, 4-day or 3.8-day half-life. Radon-222, it's all radon gas is radioactive, so from that point of view, completely unsuitable. It is the case, for instance, that in Ramsar in Iran, that in terms of natural radioactivity, that has the sort of record. Now, it's interesting to note that the medical outcomes of people that live in Ramsar are actually no different. And you might even argue a little better, frankly, life expectancy a bit better there than when adjusted for other factors. So, you know, within this sort of range. Now, there are instances, obviously, of higher exposures. I mean, you know, one that you know, puts in stark contrast and is obviously at the extreme end of radiation exposure that people are likely to suffer was the reactor building, where, of course, some of the emergency personnel responding did get exposed to this. I'm afraid at these levels of radioactivity, as you can see, it's about 8 orders of magnitude larger. Your life expectancy is very short. Now, it is also the case, for instance, with computer tomography scans, that you are typically there exposed. It depends on the procedure, but you can be exposed to as much as 10 to the 5 micrograys per hour. And in fact, if you take, certainly for a typical person in the US, that about a quarter of their total radiation exposure actually comes from medical procedures. On the average population for any individual, it may be nothing, it may be more significant. If they're using the tomography machines in a live mode and literally conducting operation, then the exposure can be really quite high. And there's an argument to say that in some cases they're probably doing more damage with the radiation exposure. But anyway, this gives you, you know, a sense of scale. Now, we of course are at the other end. We are trying to do experiments where we need to reduce the substantially below the natural radioactivity, because this is creating events per second. We need to be in a regime where we're competing with events. Now, it turns out that when you go underground, it's very dependent on the rock as to what the sort of level of radioactivity is. In the Davis cavern, which is the experiment where we're doing in Sanford lab, it turns out that the rock is actually quite low in radioactivity there. So there is some reduction over natural levels. at the Davis Cavern. But that's not because you're going underground, that's just a function of the rock we happen to be adjacent to it. Most of the reduction that occurs in terms of reducing these gamma rays, these high energy photons that are emitted during nuclear decays, actually comes, as I showed you in the extended talk yesterday, because you're in the middle of this water tank. So you have, and this is a technique that's been used in physics a great deal. The reason you use water is simply that it's very easy to purify. It's been demonstrated that you can purify water to levels where you're at a level of about 10 to the minus 18 grams per gram uranium and thorium. Now, I have to add that for our experiments, we don't have to go anywhere close to that level of purity. That requires a lot of organization, a lot of logistics to do that, but it's been done in experiments like the Snow experiment. So, but we use water, high purity water, as a shield, and by simply putting the order of 4 meters between you and the outside world, that simply ranges out all of the gamma radiation. Now, it's actually the case that the xenon, in our case, the third of a ton of xenon, is itself able to act as a sort of self-shield. And as far as event rates at low energies are concerned, the effective reduction we have in gamma, when the gamma radiation rate comes down by this huge factor. We can reduce gamma radiation as a contribution to our experiment by a very, very substantial fraction. And this is going to be important because when we run our detector, we'll be in a mode where we hope there'll be next to no photons, gamma photons, trying to deposit any energy in the middle of our detector. And if we can do that, if there is a dark matter signal, it will be very clear. Now, this is a little bit different from many of the existing experiments. Frankly, the existing experiments have not really been big enough, and therefore the levels of radiation that they have had in the middle is still significant, and you will see in the data that I'll show you that often the art, or the process that they're going through to try to look for dark matter is one in which they have conventional radiation deposition and they're discriminating against it using various methods that are available to them in a particular detector. Okay, so that was the sort of sources of gamma radiation. So I'm afraid. So in terms of units per day, in a typical human, one's looking at about 10 to the 9 radioactive decays per day. So unshielded in the range 0 to 100, the sort of figure you get is around 10 to the 7. So 7 orders of magnitude in this, higher than one event, 10 to the 7, in this 0 to 100 range. Now, for anybody, some of you may have already done a bit of work with low background counting, but of course the very traditional way to deal with backgrounds is just through lead shielding. And you can take off 5 orders of magnitude just by stacking lead bricks. It's a traditional occupation of graduate students. I certainly went through it myself. But you can, you have to be a little bit careful with the cleanliness of the lead. But you can, it's trivial to get yourself an enclosure which is, say, a factor of 10 to the 2. The question is, how do we go lower than that? Well, for instance, when we proposed the CDMS experiment, essentially we were not expecting to do very much better in terms of the electromagnetic background than this value of the order of 10 to the 2. So what we did is, and I'll show you, this is one experiment I'm going to show you, is we cunningly constructed the detectors, which were small, or sort of a third of a kilogram pieces of germanium, so that by reading out both the ionization signal and the phonon signal, that the ratio of those two signals would allow us to tell the difference between an electromagnetic and a nuclear recoil. And we were able to push that, even in the early stages, by 3 orders of magnitude, and latterly, I think, the performance numbers are now around 5 orders of magnitude. So they are able, for the most part, to completely eliminate gamma rays which are scattering on electrons. The events are still there, but they can distinguish them even at relatively low energies. Now, moving below those sort of levels, the challenge can be met. For instance, this high purity water will do you a lot better than the lead. It does just require physical space. I mean, the water tank, is as big as this room, essentially. The ones putting the detector in. But assuming you want to arrange the space, that's okay. The other thing is you do have to work relatively carefully in terms of material selection. You don't want to put ceramic or rock into your detector, if you like. So anything with a standard load of uranium, thorium, or potassium or whatever is no good. You need to be selecting towards the part per trillion level, the 10 to the minus 12 gram per gram level. Now it turns out that in plastics that's relatively simple. In metals, if you choose your metals carefully, you can move towards that. And for instance, copper, titanium, and the like, we found that we can actually achieve, those sort of levels. Now, there is another aspect, as I already mentioned. We do our physics deep. The reason for that is cosmic rays. So let me move on to discuss cosmic rays. Now, the primary cosmic rays are actually either ultra-high energy gamma rays or high energy protons, where the energies are measured in terms of, well, they can go anything up to 10 to the 20 EV, and for those of you quick at math, you'll realize that's a joule, right? So you have cosmic rays, which are enormously high. These are single cosmic rays. Now, thankfully, the ones that have a joule energy are actually fairly rare, although of great interest from an astrophysics point of view. But, more typically, they're down, obviously all the way down to sort of TeV levels. But these things are hitting the upper atmosphere and create these showers. So the cosmic rays we care about in my sort of work is actually, if you like, the secondary cosmic rays. There are a fair number of hadrons ionizing particles. Now, those are relatively trivial to shield. It is the muons that are the most penetrating and the particles that we care most about. So the only way, muons are minimum ionizing particles. They're relatively difficult to stop. In order to take a order of magnitude out of the muons, I think one's typically looking at, actually depends on the energy spectrum, but scales of 500 meters or so. So in order to achieve the kind of, water equivalent, so in order to achieve the kind of shielding that we desire, we have to go deep underground, of order 4,000 meters water equivalent, which is typically about a mile under the ground. Now the flux levels, as I say, a mile underground, it's actually a little bit more than one per year. It's probably 3 or 4 per year per hand when you're a mile underground. So that's how we achieve that. Now, again, just to give you a sense of perspective on this, and this is something people don't always recognize, is that, for instance, if you are at sea level, then measured in, again, sort of radiation dose terms in terms of microgray per hour, this is the value, this 3 × 10⁻², at sea level. So as you can see, in absolute terms, it's not a significant, radiation as significant as the local radiation. Now, if you were to be above the atmosphere and a solar flare occurred, and obviously this is one of the big problems with any kind of Mars mission, is that during such a flare, the radiation rates climb quite dramatically. Typical exposures are about 50 during a regular spacewalk, no solar flares. Now, it is interesting to note that when you're on a plane, the activity levels are significantly higher, and I've actually taken a Geiger tube on a plane. You can attach them to your PC and you can measure this quite nicely. It's fairly entertaining. Of course, you get a lot of people asking you what the hell you're up to these days. But one of the things it means is that, for instance, we can't fly certain components because the cosmic activation that you get simply by taking a piece of material and putting it at 35,000 feet is sufficient to give you a problem in terms of, for some materials there are radioactivity, there's activation that occurs due to those cosmic rays that takes long enough to cool down again that you actually don't fly them, you drive them. Now, underground, and I think I mentioned this number to you already, we're getting about over a factor of 1 million, 3 or 4 million suppression compared to typical sea level values by being a mile underground, and that is why we are a mile underground. I should just lastly mention neutrons. Now, why do I care about neutrons? Now, neutrons are emitted from natural radioactivity. They're also a byproduct of cosmic ray interactions in material. They blow nuclei apart. Why we care about them is because neutrons, their primary mode of interaction is via nuclear scattering. So they look, to all intents and purposes, on an single event basis, like a cosmic, like a muon, like a WIMP. A dark matter particle. They will cause the same kind of recoil, and they will do it in roughly the same energy regime as well. And because of that, for dark matter experiments, you must keep neutrons out of your experiment. Now, all is not lost in the sense that if you do get a neutron into your experiment, if your experiment is relatively large, the typical interaction length for neutrons of energy of order 1 MeV, which is the kind of neutron that's going to deposit energy in your detector in the regime we care about, is 5 to 10 centimeters. So if your detector is relatively large, you'll in fact see the interaction scatter more than once. Now, there's no way that a WIMP can scatter more than once. It's difficult enough to get it to even scatter a single time. So if you see 2 scatterings occurring in your detector at the same time, that tells you that you have nuclear recoil event, but it must be due to a neutron and not due to a WIMP. And relatively speaking, again, in terms of absolute radiation dose, neutrons are insignificant. But in terms of dark matter experiments, because they can look like dark matter, they're particularly important. So what you actually find is that we're able, through the expedient of again, water is a very good moderator and will actually absorb the neutrons through capture, but the primary thing we care about is their moderation. They moderate the neutrons just through hydrogen scattering, bringing the energy of the neutron down to a level that we don't care any longer about. But we're able to reduce the effective energy deposition rate to limits that are substantially below. So our main neutron problem comes if we just simply screw up and put a material into our detector that has enough uranium or thorium in it to be emitting. There is also another effect that is worth considering, which is if you have an alpha emitter, if the alpha impinges on a nucleus that is relatively light, anything substantially lighter than iron. So, for instance, in our experiment, we have a fair amount of fluorine in the Teflon, the PTFE. Alphas that are deposited on the surface of the PTFE, radioactive material such as radon, for instance, or a daughter of radon, if that's deposited on the Teflon, you have to be a little bit concerned about that. Now, for reasons I can't go into, actually in our experiment we can deal with this. It's not a fundamental problem, but in one or two of the other experiments, because of the way they work, this business of radon as one of the classic examples of getting into your experiment while you're working on it, when you're initially putting it together, and depositing radioactive daughters in tiny numbers. You're talking sort of millions of particles. So it's quite a tough. It's a very small amount of radioactivity. That's enough to start generating neutrons at the level that are actually going to give your experiment a problem. So for those of you that are digging down deeper in this stuff, you will. That's one of the backgrounds that you will see discussed. So, as I said, these are all underground sites. This figure of merit I've shown here. I didn't show it for the other sites, but that is the amount of cosmic ray effective shielding that is provided by all these sites. So all of the dark matter experiments I'm going to talk about are located at one of these experiments. So let me sort of go in immediately and now talk. Yes, I must start talking about some of these experiments. So let me talk about the CDMS experiment, for instance. It's been around for a long time. It was based on a very elegant idea that you can read out. Well, let me show you
Sorry, there it is. No. So the element of the detector, it looks like this. This is a 7.5 centimeter diameter, 1 centimeter thick. They're actually getting bigger now. The run they've just started now actually has devices which I think have gone to 3 centimeters in thickness, still 7.5 centimeters across, 3 centimeters in thickness. And on the surface has been patented, and I actually spent 1.5 years in a clean room making these bloody things. It's quite entertaining, so I don't know how many of you have had a chance to work with sort of thin film wafer systems, but of course they're really designed for the standard 600 micron silicon wafers or the like. But you take a 1 centimeter thick wafer of germanium, which is obviously a lot denser than silicon, and put it on one of the spinning and press the button. You have to duck if the vacuum fails. This thing comes off like a frisbee. Anyway, we used to carry gloves around it when it started. We began to realize what did not work. So anyway, what was going on is you were depositing thin films of aluminium and tungsten on the surface, and you would cool the entire crystal down to below 100 millikelvin. At those kind of temperatures, the tungsten, the active element, actually becomes superconducting. And it's known as a TES, a transition edge sensor. And in fact, what you do is you voltage bias these transition edge sensors. In fact, there are 1,000, depends on the design, but there's 1,000 of them, all integral to this pattern in 4 parts. There's actually over 4,000 in total on these things. They're micron scale wiring. They're all wired in parallel, and they are held by voltage bias on their transition temperature, their superconducting transition temperature. When when a particle interaction occurs in the middle, it sends phonons out through the lattice. Those phonons go into the superconducting films on the surface of the detector, and they warm it up. They warm the metals up very slightly, and the transition characteristic, the superconducting state, is slightly disrupted. Because you're voltage biasing it, what happens is a modest change in current. A modest change in current occurs. But if you arrange with squid electronics, you can actually see nanoamp changes in current, and because all of these things are in parallel, all the current changes add together, and you get a really quite substantial signal. Partly because what we were doing was using arrays of squids rather than just a single squid, so that also provided significant amplification of the signal. And it's a system that works, when it wants to work, it works very well. So what you do is you read out that phonon signal through these transition edge sensors on the surface of the part, but at the same time you read out the ionization, the charge signal, using very conventional, just 2 electrodes, top and bottom, and you put a voltage bias across it. Now, because you're very cold, you don't need to deplete the semiconductor in the same way, so you can actually use just a few volts to collect the charge. You don't need to use kilovolts as you would if this this material was at room temperature, also 77 Kelvin or like. So that's really how it operates. And for a nuclear recoil, well, let's start with it. For conventional electron recoil, which is just from a gamma interaction, you get this amount of phonon and this amount of charge. The two are pretty close to proportional over the energy ranges we care about. If you have a nuclear recoil, the amount of charge is substantially less. You can talk in terms of the Lindhardt effect, or we could talk, if I had time, about the microphysics of the way in which a nuclear recoil deposits energy into the lattice. But this is the empirical result. The charge versus the phonons. Essentially, you see all of the energy in the phonons. You just don't see as much in the charge. So what does that look like in practical terms? That's shown here. If we plot the ratio of the ionization signal divided by the phonon signal, and then just talk about the energy of the event here, then when the ionization yield is high for the electron recoil events, you get events up here, and then when it's for a nuclear recoil, this is a case of californium source, so you've got neutrons interacting in your detector. That's shown here. So that's it. It's as simple as that. Now the only thing you care about, essentially, you've got very good separation, very good discrimination. And really the only thing you sort of care about, you see these events here. This is the barium source, which happens to be 356 keV gamma, whatever. Some fraction of the events, the ionization yield you're measuring is not quite, 1. It's not the normalized value. What are you going to do about that? That's actually occurring because of events near the surface, and this is a common theme. When you have detectors, you can't, things that take place at the surface are not as reliable as what happens in the bulk. This is not uncommon. So, I'm going to have to go a little bit faster, so let me think. So what do you do about it? What you do about it is you try to use some other parameter from your detector. Now, it turns out that the phonon signal that you get from the transition edge sensors is actually quite fast. You're not just measuring a temperature rise, you're actually seeing the leading edge of these phonons which are propagating at sort of kilometer per second velocities, that you actually see a sort of rise time as the phonon signal goes into these sensors. And it turns out that for surface events versus, say, for example, a nuclear recoil event in bulk, for a surface event, this is, say a beta particle, an electron, which is just scattered in the surface of the detector, but the phonon rise time is faster. Now, this was one of the reasons why this transition edge technology was selected, because it was possible to do this. So you've now got an additional parameter. These events here may be surface events, but you can now differentiate them because you have this faster rise time in the phonon signal, even though the ionization is degraded. So you can remove these events using a rise time cut. So this is, whether you be in a particle physics experiment, an accelerator, or whether one is a rare event search like this idea of doing cuts of various types, various parameters, is one you get pretty used to. The problem always is, how well do you understand your cuts? Because at the end of the day, if you want to claim discovery of a particle, you better be fairly confident that you've not just simply left some events behind from your more conventional background sources. So this was an example of data. This is the region where they're looking for dark matter. They are, in fact, I hasten to add, this data was taken sometime after I left. This is the region where you'd expect to see dark matter signal, and they're using this technique of blinding, so that when they're designing the cuts in the detector, they do so in a way that doesn't, that they are not influenced by the acceptance of their modification of the cuts. You don't want to, because frankly, if you're running an experiment, you want to hire good people, right? And the thing about good people is, they're smart, and if they're perceptive, and if they know this is a little bit ironic, but if in a sense you want your detector to do really well, and by really well it means not seeing any dark matter, because we're in this slightly negative mode of trying to get rid of backgrounds, people can overdo it. They could end up cutting the data so aggressively that they actually remove potential signal, because they want to come back and say, look, I'm the smartest kid on the block, and I've managed to make this detector perform better than anybody else's analysis. What may have happened is you've just been clever with your cuts, and you've essentially removed too much sensitivity from your experiment. You want to have some confidence that when you unblind this region, that what is in there is statistically it's reasonable. So they went ahead and unblinded it. Now, what I'm showing you here is the data with all of the surface events, but of course we have this timing cut. So they put the timing cut in, and it very substantially, and various other cuts as well, but it very substantially cleans the data up. So, and this is aggregating all the data across many detectors. So what they did in fact find was that they had a couple of events, and then the debate ensues. Is this dark matter, or is this what we tend to call leakage, or events? And because these are relatively low energy, well, of course, this is where you expect to see dark matter, but it's also where you're struggling a little bit with signal to noise. So you're always in this situation that could this be? Now, of course, what they did is they made an estimate of how many events they expected to leak with all their cuts, and then the estimated was about 0.8. So in this situation, with this particular result, you have a net result of expecting about 0.8 events to be leaking into this region, and you see 2. Now, for those of you that are quick on the mark or used to doing statistics, that represents about a 20% likelihood that you would have a fluctuation if you have an expectation of 0.8 and you actually see 2. So that's not discovery. We don't rush around saying that that's a discovery. Of course, one of these or both of these events could be WIMPs, but since Occam's razor, if you like, or the simple approach, if you have a background estimator which says you should have 0.8 residual leakage events at that energy in your detector, then it's probably a thing. So what are they doing? Of course, they've built a bigger one. They have more mass. They've gone to thicker detectors. They've actually, interestingly, modified the electrodes. So I think, frankly, they're going to work better. And this is where they are currently, and they hope at the same location in Sudan to do substantially better with these larger detectors. So that's the CDMS experiment, and they may indeed get even bigger to 100 kilograms, possibly at snow level, although that phase of the experiment is yet to be approved. Let me talk. I've mentioned Dharma and Libra. I wanted to spend a little bit of time on that. This is the great. Well, I was going to say granddaddy, but it's really the great grandmother of dark matter experiments. I remember back in 1989 when they made their first announcement, and they made an announcement unlike any other in that they said they have evidence for dark matter. And the evidence they had is, I've tried to sort of illustrate schematically here. So I thought I'd put a recoil spectrum in there as well. It doesn't. Okay, I'm going to have to. Sorry, I'm not sure where it's gone. Okay, what they have is an array. This is a terrible schematic, but it's nice and simple so you can understand. They literally stacked sodium iodide, 100 kilos of it in the first instance, 250 kilos of it in the second Libra experiment. And they watch it with photomultiplier tubes. So they put 2 PMTs, one at each end of these each one's about 10 kilos. And by using 2, they can demand coincidence between the 2 photomultipliers. So when you get a particle event in the sodium iodide, light goes in both directions, you pick it up in both PMTs, and that allows you to reject events that are just due to noise in one or other PMT. And so it's very simple experiment. It's very, very, very well put together. And they use sort of conventional shields of copper, lead, and polyethylene, around the outside. So it's very standard exposure. And then they have to make sure that the gas, any gas in here is very low in radioactivity. So they use a nitrogen purge to avoid radon. And what they're looking for is the effect I mentioned yesterday, because of the in June. Although the Earth is tilted somewhat compared to our velocity vector towards Cygnus as we go around the Milky Way, nonetheless 15 kilometers per second lines up with this component, so you have a velocity that's modulating plus 15 in June, minus 15 in December. What that does is it produces a small modulation, but just to put that in context, so what I'm showing here is the event rate in the sort of low energy bin, the low energy recoil bin of that detector. So if you add all of the events that are occurring in the lowest energy bin of each of these detectors. And you just watch the rate, and every week you have a number, and you record that number and record a new number next week and next week. And what you find is that the rate is oscillating very slightly. We almost can't see it here. It's moving up and down. So what you suggest is that, yes, we have some background in our detector, but we also have a WIMP signal. And the hypothesis is that the background does not modulate. It doesn't have any reason to go up and down with the seasons, with June, December. So that it is the WIMP signal. So somewhere in there is a WIMP component that is generating this overall, and the modulation is of the order of 2%. Now, how reasonable is it to say that your background doesn't modulate? Now, of course, there are many ways you can, in fact, modulate a background. Cosmic rays, for instance, just because of the change in temperature of the atmosphere, they modulate all the time, and unfortunately tend to do so with the June-December phase. The amount of groundwater in your laboratory changes. That changes the characteristics of the rock. That will change the emission of neutrons or gamma rays. So that there are, frankly, we use a lot more electricity in the winter than we do in the summer, which means if you don't design your electronics correctly in terms of regulators and monitoring, you can find your entire data acquisition system is going up and down. And one of the things I did as well, immediately after graduate school, my first postdoc, I was involved in an experiment where it turned out we were critically trying to measure the existence of a 17 kilovolt neutrino, which none of you will have ever heard of, but it was a kind of bizarre suggestion. Thank you. Anyway, it required incredibly. I learned a lot about systematic control of data acquisition systems. Just moving into the digital domain does not guarantee integrity, especially at that point you go from analog to digital. You must understand in detail what is going on there, because you can introduce effects. And again, I would love to talk in detail about all the sort of effects that would concern me in such an experiment. I will say that personally, I don't believe the Dharma Libra experiment has adequately addressed all of those systematics. I still think it remains for them to demonstrate that their control of their instrument is actually good enough to be making the claims they are. Nonetheless, if you look at the data, it's wonderfully compelling. This is the data. So, you know, we go back to, what is it, 87, I think it was, and all the way through to the, to the current day. So it's a long-running experiment, and what we're showing here is this is the average number of counts in the lowest energy bin, or lowest energy bins, and then you can see this rate modulating, and this is the data, and this is the fit. And, you know, there's no denying, you can see a modulation there. It's an over 6 sigma. I don't think there's any doubt that that residual rate is modulated. The primary debate is that due to a WIMP component in the detector, or is it just due to the background somehow being modulated? So that is the Dharma experiment. Now I'm going to have to jump slightly because I'm a little bit behind. Actually, I haven't even looked. I wanted to do a little bit of physics with you on the xenon system, but I'm going to go straight to the Zeppelin-3 experiment now, which of course is one that many people here at ITEP, of course, are familiar with because it is an ITEP experiment. It was conducted at the Bolby underground mine, and it is a two-phase xenon detector. It uses a liquid xenon target in the same way that Lux or Xenon are now doing, and you see both the light and the ionization. And as I said, it's conducted in the United Kingdom in a laboratory known as Bolby. Now, the way it was designed, so this is the sort of engineering profile, and these are the photomultiplier tubes, and this is the xenon. And these are the grids. So that the innovative part of the design here was that it's actually everything's in a pancake, which means the grid separation is relatively small. And the reason for that was that the experiment was designed to explore what would happen in liquid xenon as you go up to very high fields. So that you could, by applying of the order of 20, 30 kilovolts, because the drift distance is relatively modest, you could actually get a very high field per centimeter. As it turns out, we have reason to believe that the physics of xenon would change significantly with changing field. It changes a little bit, but probably I think the conclusion from the running is that physics probably doesn't change enough, to make it necessary to operate in that extreme high field regime. So this is what this top surface, the photomultiplier tubes look like, and once the lid and confinement is on, then it's filled with liquid xenon, and it's the liquid xenon in this region here, which is the one that's directly observed by the experiment, and where you're looking for particle interactions. So okay. So this was just a timetable of the runs. There were two major science runs, one in 2008, the first science run, and the second science run took place last year, at the end, the middle of 2010 to the middle of last year. Gosh, I'm sorry, I'm a little bit short of time. What should I say here? Let me just make sure so you understand the experiment. So again, the shielding is essentially designed with a great deal of copper. A lot of care was taken in order to use materials which are very low in radioactivity, but also there were concerns about the contamination of the xenon itself and how that might affect the functioning of the detector. So in terms of materials inside the cryostat, they ensured that there were very few foreign materials, a very modest amount of Teflon, and otherwise it was essentially copper and the grid material and the photomultiplier tubes. And it uses the same idea of having both a lead and a polyethylene shield, and also a cosmic ray veto, so that any residual events associated with cosmic rays will be filtered out. Now, if you look, this is looking directly down, as it were, on the PMT structure, and again, I'm afraid I've got too little time. But what you can do is you can localize events. Because of the pancake design, you can localize events both in the S1, the primary light signal, but also in the secondary light signal for the electrons that jump out of the liquid. And you're using the ratio of the S2, the ionization signal, to the primary signal in the same way that CDMS does, in the same way the other experiments do. It's that ratio that tells you something about the nature of the interaction. You can tell the difference again between nuclear recoils and electron recoils. What you also do, and this is typical of these kind of experiments, is you go through, based on your screening, you make an assessment of all the radioactive backgrounds that could be contributing to events. You also care, this is sort of on the edge between condensed matter and sort of particle physics, but one of the things you care about is the light yield. How much light is generated, how much ionization is generated per unit energy deposition. So this is actually data points not just from Zeppelin-related calibrations, but actually many calibrations throughout the field, trying to understand, as you go from high energies to low energies. In this case, on the right, we're talking about primary scintillation. So we're measuring, we have a relative scintillation efficiency defined relative to electron recoils. So this is a plot essentially when nuclear recoils occur in a detector. How much light do you get in primary scintillation? Now, it is a little bit, it's less than the amount of light you get for the same energy for an electron recoil event. And there is, if you go to a conference, you'll see there's quite some debate about exactly what the function versus energy of this. And it's relevant because dark matter is done at low energies, and therefore you want to know how much light is being generated. In addition, what's interesting to note is that the ionization, the amount of electrons you get in the liquid and that is detected as this secondary signal, interestingly, that actually is shown to, and there's general agreement on this. This region here is far more contentious than primary light. For the secondary signal, you actually get more ionization the lower energy you go, which in itself is a very interesting phenomenon. Again, I'd love to talk about it. Okay, so we have the physics result, which the middle of last year was actually is very competitive with the other experiments going on. Zeppelin 3, has beaten CDMS2, which is the sort of was the great granddaddy, if you like, of the field with its latest results. And this has been possible both in spin independent and also what's known as spin dependent. It turns out that dark matter may couple simply through some sort of scalar interaction to all the nuclei, but it may actually care about the spin state of the nucleus, in which case certain materials are better than others. Xenon, 50% of the isotopes in xenon actually have non-zero nuclear spin. For a number of other targets, that's not the case. They're either even nuclei, or they have a very small component of odd spin nuclei. So you end up with a so xenon there is xenon target is very competitive compared to germanium. Now, obviously, xenon 100 result came out, and because they were using a larger mass. Same technique, but that has actually allowed them to push the sensitivity even further. And that actually, I found this slide. This also mentions actually the work of Dolce and all from 1970, which really, in a sense, is credited as starting this incredible series of development right through to Dmitry Akimov, who was here yesterday. Unfortunately, he's not here today, but you know, the work that he and others have been very directly doing with the Zeppelin program. Have I got 5 minutes? I've got 5 minutes, thank you. Okay, so choices. I have more material than 5 minutes. Which one should I go talk about? Ooh, choices. Sorry, I want to use this widely. Okay, I said I was going to mention gas detectors yesterday, so I ought to follow through on that one. I was going to show you another angular modulation result, but mainly because, for those of you that are familiar with statistics, it's one of these classic examples of I think, the cart getting before the horse. The statistics aren't yet, I think, there for the angular modulation. We'll talk about that offline if you want to. So, where are we going with dark matter? Now, dark matter interactions are frighteningly rare. You know, we're already at the 1 per kilogram per month level. But what if we do discover dark matter? And you know, as I say, I'm fairly confident that we have the right tools to do this. These large detectors are potentially going to be able to filter out all the other competing events, and we end up with just if there is a dark matter signal, a residual number. The event rates are probably going to be at the 1 per 100 kilograms per day, or 1 per 1,000 kilograms per day. It's going to be a pretty small interaction rate. But just supposing we have found the dark matter, what are the things you'd like to do with it? One of them is, I think, to convince yourself that you really do have dark matter. It would be very nice to demonstrate that the dark matter is indeed coming at us from Cygnus because of the motion of the sun around the Milky Way. So, now the way you could do that is either through angular modulation, because that just shows you this kinematic wobble that you get through the Earth going around the sun. But the even better signal is just literally that these recoils the dark matter tends more often to come at you this way because you're going through the snowstorm. So how would you do that? It really, frankly, in solids and liquids it's probably not possible, but in low density gases, when a nucleus of 10 keV or 50 keV recoils, if you're at a tenth of an atmosphere, the recoil track lengths actually become long enough to be able to resolve if you're capable of 3-dimensionally or 2-dimensionally imaging the track, and that's exactly what people are doing. The only downside is, I just said, low pressure gas, right? So if you're trying to get a ton of target and you want to do it in low pressure gas, oh dear, you know, because volume of 1 meter at a tenth of an atmosphere, that's about equivalent to 50 grams or something like that. So you're going to need a lot of that. So you end up filling a room this size with